Out there in the vast expanse of the cosmos, there exist celestial objects that defy easy categorization. They are neither stars nor planets, occupying a fascinating middle ground. These enigmatic objects are known as brown dwarfs, often referred to as failed stars. Brown dwarfs are cosmic entities that blur the line between stars and giant planets. They are more massive than planets, but not quite massive enough to ignite the nuclear fusion that powers stars. This lack of sustained nuclear fusion is what earns them the moniker failed stars. Their existence was first theorized in the 1960s, but it wasn't until 1995 that the first brown dwarf was definitively observed. This discovery opened up a new realm of astrophysical study, offering insights into the processes of star and planet formation. The study of brown dwarfs has become increasingly important in our quest to understand the universe. These intriguing objects hold clues to the mysteries of star formation and the prevalence of planetary systems beyond our own. The birth of a brown dwarf shares similarities with that of a star, beginning with the collapse of a dense cloud of gas and dust within a nebula. Gravity draws these particles together, causing the cloud to contract and heat up. As the core of this collapsing cloud grows denser and hotter, it reaches a critical temperature and pressure. For a star, this marks the point where nuclear fusion ignites, flooding its surroundings with light and heat. However, a brown dwarf doesn't accumulate enough mass to reach the necessary temperature and pressure for sustained nuclear fusion. Its core, while hot, remains relatively cool compared to a true star. Without the outward pressure generated by nuclear fusion, the brown dwarf's core continues to contract until it reaches a state of equilibrium. At this point, it ceases to collapse further, but remains a dim object, emitting a faint glow primarily in infrared wavelengths. Brown dwarfs occupy a fascinating middle ground between stars and planets. Their mass sets them apart from both categories, creating unique characteristics. On the one hand, brown dwarfs are more massive than even the largest gas giants in our solar system, such as Jupiter. Their immense size and gravitational pull distinguish them from planets. On the other hand, brown dwarfs lack the mass required to sustain hydrogen fusion in their cores. This fundamental difference prevents them from shining as brightly and consistently as true stars. Their intermediate nature presents a challenge to traditional classification systems in astronomy. Brown dwarfs don't fit neatly into either category, highlighting the diversity and complexity of celestial objects. Despite their failed star label, brown dwarfs are far from failures in the grand scheme of the cosmos. They represent a crucial link in our understanding of the formation and evolution of stars and planets. Brown dwarfs exhibit a range of sizes and temperatures influenced by their mass and age. Despite their name, they are not always brown. Their color can vary depending on their temperature. In terms of size, brown dwarfs are typically larger than Jupiter but smaller than the smallest stars. Their radii can range from slightly larger than Jupiter to about 70% the radius of the Sun. The temperature of a brown dwarf is directly related to its mass and age. More massive brown dwarfs retain more heat from their formation, making them hotter than their less massive counterparts. Younger brown dwarfs tend to be hotter than older ones because they are still radiating away residual heat from their formation. As they age, they cool down gradually, emitting less energy. The temperature of a brown dwarf determines its color. Hotter brown dwarfs may appear magenta or orange, while cooler ones emit a deep red or even a faint purple hue. Section 5. The spectral dance of brown dwarfs. Astronomers classify brown dwarfs into different spectral types based on their temperature and spectral characteristics. These classifications provide valuable insights into their properties and evolutionary stages. The most common spectral types for brown dwarfs are L, T, and Y dwarfs. Each type represents a distinct temperature range and set of spectral features. L dwarfs are the hottest type of brown dwarf, with temperatures ranging from about 1,300 to 2,000 degrees Celsius, or 2,400 to 3,600 degrees Fahrenheit. Their spectra show evidence of metal hydrides and alkali metals. T dwarfs are cooler than L dwarfs, with temperatures between 700 and 1,300 degrees Celsius, or 1,300 and 2,400 degrees Fahrenheit. Their spectra exhibit methane absorption bands, indicating the presence of this gas in their atmospheres. Y dwarfs are the coolest type of brown dwarf, with temperatures below 700 degrees Celsius, or 1,300 degrees Fahrenheit. Their spectra are dominated by water vapor and ammonia absorption bands. The classification of brown dwarfs into spectral types helps astronomers understand their physical properties, such as temperature, composition, and age. This information is crucial for studying their formation and evolution. Section 6. Lurking in the cosmic neighborhood. Brown dwarfs are not as rare as one might think. In fact, they are surprisingly common in our galaxy, the Milky Way. They lurk in the vast spaces between stars, often hidden from view by their dimness. Astronomers estimate that there may be as many brown dwarfs as stars in the Milky Way. However, their faintness makes them challenging to detect. Most brown dwarfs have been found relatively close to our solar system, within a few hundred light-years. This proximity makes them valuable targets for study. Some brown dwarfs have been found orbiting stars, while others appear to be free-floating, not gravitationally bound to any star. These rogue brown dwarfs wander the galaxy alone. The discovery of brown dwarfs in our cosmic neighborhood has significant implications for our understanding of star formation and the prevalence of planetary systems. Section 7. Windows into star formation. Brown dwarfs play a crucial role in our understanding of star formation. Their study provides valuable insights into the processes that govern the birth of stars and the factors that determine their ultimate fate. The formation of a brown dwarf represents a pathway that diverges from the path of star formation. By studying where and how this divergence occurs, astronomers gain a deeper understanding of the critical factors influencing star formation. Brown dwarfs provide a glimpse into the conditions that exist at the lower mass end of star formation. They offer clues about the minimum mass required for an object to ignite nuclear fusion and become a star. The study of brown dwarfs also helps refine our understanding of the initial mass function, which describes the distribution of stellar masses at birth. This function is fundamental to understanding the evolution of galaxies and the universe as a whole. By studying brown dwarfs, astronomers can piece together a more complete picture of star formation, from the initial collapse of gas and dust to the diverse outcomes that result. Section 8. Brown dwarfs and the hunt for exoplanets. The study of brown dwarfs has implications for the search for exoplanets, planets that orbit stars other than our Sun. Brown dwarfs can serve as both companions and obstacles in this exciting field. Some brown dwarfs have been found orbiting stars, much like planets do. These brown dwarf companions can provide valuable information about the star system, such as the star's mass and age. However, brown dwarfs can also complicate the search for exoplanets. Their gravitational pull can mimic the signal of a planet, leading to false positives in exoplanet detection methods. Despite this challenge, brown dwarfs themselves can host their own planetary systems. In fact, some astronomers believe that brown dwarfs may be ideal locations for the formation of rocky, Earth-sized planets. The study of brown dwarfs and their potential to host planets expands our understanding of planetary formation and the diversity of planetary systems in the universe. Section 9. Unlocking the secrets of brown dwarfs. The future of brown dwarf research is bright, with new technologies and telescopes poised to revolutionize our understanding of these enigmatic objects. Next-generation telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, will have the sensitivity to observe brown dwarfs in unprecedented detail. These telescopes will allow astronomers to study the atmospheres of brown dwarfs, revealing their composition, temperature, and weather patterns. Advanced imaging techniques will enable us to directly image brown dwarf companions to stars, providing valuable information about their orbits and interactions. The study of brown dwarfs is a rapidly evolving field, fueled by technological advancements and the insatiable curiosity of astronomers. As we continue to explore the cosmos, brown dwarfs will undoubtedly continue to surprise and intrigue us, shedding light on the mysteries of star and planet formation and the vast diversity of the universe we inhabit.